All right. So good afternoon, everyone, and thank you for being here. It's really a great pleasure to have Sasha Panfilov here, as a longtime collaborator, my former PhD advisor. So Sasha is, he has a degree from the Moscow Institute of Physics and Technology, then got a PhD in biological physics from Pushina Institute. He has traveled quite a lot after that. He's been in the States, in Utah, Salt Lake City, for a couple of years, before then coming back to Europe in Netherlands at the University of Utrecht, and then finally settling at the University of Ghent, my home university, where he is a professor of biophysics. He's now emeritus professor. And he's also a visiting professor or guest professor at the Leiden University in the group of Daniel Pijnappels. For those of you who may know him, works a lot on cell culture, optogenetics and stuff. So Sasha is a world-leading expert in cardiac modeling, whole heart modeling, but also some major discoveries in dynamics of spiral waves, reentrant arrhythmias. And so today he will talk about the role of fibrosis in cardiac arrhythmias and how we can model this. So, Sasha.
Okay. Thanks a lot, Olivier. I mean, I kind of checked my computer, and I was here, I think, 5 or 6 times, but I did talk only in 2012, very long time ago. And since that time, I had a lot of work has been done, and I mean, and I cannot tell you about all what happened during that years. But for today, I don't know whether it meets your expectations. I decided to present a rather technical work, which will not have all what Olivier mentioned, like whole heart modeling, etc. Because one of my aims to visit you here to discuss our interest in fibrosis and in modeling fibrosis. Therefore, I will present mostly on some of our work on fibrosis, not all some of our work on fibrosis, but still I want to show a few slides from another research line which we do in Daniel Pijnappels' group, just 3 slides, because I understood that not everybody of you saw this paper. In a way, if it will be just a teaser, but maybe we will also present these results in more detail, maybe at some later stage. Maybe also Daniel comes with me or by himself and tell you about that. And therefore, I want to tell a couple words about this work, what we published a couple years ago in eLife. And it goes about very interesting idea what Daniel has. This idea, is it possible to restore cardiac rhythm without any drugs, without anything, just by inventing a new ion channel, which will do it? And basically, when I started to work on that project, he told me, Sasha, can we invent some ion channels which will not work at normal heart rhythm, but which will work only when arrhythmia starts? It will stop arrhythmia and then shut down again. And because this is a teaser, I don't give you any details, but it took us quite a long while. But we developed several models, and in this paper, they are all purely mathematical. There are 3 mathematical models presented in that paper, which exactly do the same, and just illustrate probably the only whole heart model which is present here, like 2 hearts, one with expressed channels, one not, left with channels, right without these defibrillating channels, and then this channel somehow detects arrhythmia, but it's just normal channel with Hodgkin-Huxley kinetics and so on. And then it activates, and then arrhythmia disappeared, and you have back sinus rhythm at the left-hand side, and like at the right side, you have VF. And in this paper, there are also some sort of a little of experimental proof that this can work on real cells using some type of dynamical patch clamp protocol. But anyway, this is very interesting work for me, and we continue work on it, not as fast as I would like, but I think it's interesting and unusual direction of research. And this is what I wanted to tell about this general thing. Now I want to talk about fibrosis modeling. Basically, for the first time for this talk, I looked to my CV, wanted to identify papers which are devoted fully or partially to the fibrosis modeling, and I found like 19 papers. Therefore, of course, I wouldn't tell you about all research which was done here, but I would like do it, I mean, with some informal stories and some of results which may be not very widely known. But I will start with diffuse fibrosis, and my first, when I really started to model fibrosis as a fibrosis came in such sequence. Like one of my very first papers where we found spiral breakup was done, I don't know, okay, very long time ago. And then later on, we developed another model in which you will have this breakup. I think you saw a lot of such pictures, don't want to tell you more. And then, of course, we put this model to the whole heart and also found a similar process of formation of fibrillation in the human heart. It's a really old movie, I don't know, like something like 93 or whatever. And then such situation happened. One of my students who actually was working in my group together with Olivier, Christian Zimlin, he was working in my group, and at that time, Leon Glass invited me for one conference in Canada about cardiac modeling. It was a very good conference. But I couldn't go because I had to teach a very big course at that time, and I did, but only once in my life. I prepared my talk, but asked Christian to present it. Okay, and Christian went to that conference. I don't know, but Olivier was at this conference. Oh, yeah. Okay, then we can tell. And then when I wasn't present, maybe Olivier can tell better, but then when Christian started presenting it, Natalia Troyanova stood up and told, all what you're doing is wrong. All this computer artifact, my student did it, and he found that all this breakup is due to numerical errors, due to grid effects, etc., and so on. And Christian was so disappointed that he kind of could not respond here properly. But for me, it was also because I knew that this is not artifact, because I very carefully checked. But still, after that thing, I thought, okay, maybe I need to recheck it and see, do really some numerical artifacts would affect my results. And then it started new line of research, where I indeed first what I did, what most of you maybe do more than know, you can just change space step, which is the most difficult in numerical simulations. But if you change space step in explicit numerical schemes, this is basically the same as you change coupling coefficients between cells. You just make, roughly speaking, you change a number of gap junctions which cell together. And then what I did, I just took my breakup model and started studying with larger and larger space step. And what I got was completely unexpected result for me, because I would normally expect that I would have maybe more breakup, blah, blah, blah. But what I got was exactly opposite. I had a less breakup in that situation. And this I can show you one of the old simulations, where you see it's very, a lot of broken connections, or we can say fibrotic cells. And this is the same model, but you don't see any breakup here at all. And the result was exactly opposite from what I expected. And why it was also very unusual for me, because You probably know that in many cases, like this breakup occurs due to some kind of dynamic instabilities, which occur when you have a steep restitution curve. What I showed here, and basically idea of breakup that small perturbations start to grow due to steep restitution curve. And you can think if you have fibrosis, this is for sure will be a big disturbance for wave, and then you should have more breakup, but we got less breakup. And answer turned to be out extremely simple, which means the following. This is restitution curve, and this I show normal cardiac tissue, where you have steep restitution curve and you have breakup. But what happened in fibrotic simulations, just diastolic interval became longer due to this zigzag propagation, and then all this breakup disappeared. And it was amazingly solid effect. We observed it in all, basically in all models what we studied, in 3D, in the whole heart. And this is the first basically story what I wanted to tell you, that this first result, what we found, that fibrosis, maybe not bad, but for some mechanisms of arrhythmia, it can stabilize arrhythmia by decreasing instabilities, for example, and removing dynamical instabilities. Okay. But by the way, okay, we also discussed it with Natalia and found what blah, 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 doesn't matter. But still, this, yeah, thank you. But this situation fired back to me after several years. Actually, if you know, there is another famous modeling group in California at UCLA by Jim Weiss and Alan Garfinkel. And then, I think in 2012, they published paper in GCI, General Clinical Investigation, what was the first paper, also with whole heart modeling and with this breakup. And they did not cite my work. And I know them very, very good. They are my very good friends, were and still now. And I met Alan at one of conferences and asked, Alan, but why did you did you cite? Because I presented it in your lab several times. Sasha, but Natalia thought that this was an artifact. Yeah, but yeah, I don't know. Anyway, but what I want to go first and tell you, but I was wrong that this was my first study of fibrosis, because later on I found that my old research, what I did even before that, was also somehow related to fibrosis. And I can show you, a paper with, how to say, very old publication, yeah? Just one of my first papers, what I did with Arkady Pertsov, where we found that if you would have some kind of an obstacle, and if wave propagates, for example, along the boundary of this obstacle, it can detach from this obstacle and form re-entry. This work became studied in experiment, also very famous papers by Candida Cabo, where they found in experiment that if you have cut in cell culture, you can get this type of re-entry. But we also continue this research where we found that if you have like many obstacles, and if you base tissue with high frequency, you can get formation of new sources around that obstacle. However, what we found that period of pacing should be extremely high. It should be as high or even maybe higher than the shorter than the period of re-entry itself. And then we revisited this work a little bit later with Rupa Majumdar. By the way, I just tell already some of you, but want to tell that Rupa Majumdar is my former postdoc, and she's now working close to you at Nantes at Cardiac Research Institute. And she's also very good researcher. She does modeling, and would be good if you will be in contact with her, at least maybe invite her for seminar or whatever. But we did revisit it in later, and we did exactly the same. We had an excitable obstacle and paced it with high rhythm, and we found excellent agreement with previous results. Here you're supposed to see two lines, one period of spiral wave and one critical period after which you can get formation of these new sources. And you see almost for all parameter changes, they almost coincide with each other. Therefore, it seems that in order to induce arrhythmias around inexcitable obstacle, I would say, like with a lot of this infarction scar, because it's not exactly infarction scar, it doesn't have ionic remodeling around it, you still need very high frequency. And we also have a mechanism of this. If you will be interested, I can tell you later after my talk. But this is also another story what I wanted to tell you. And this translates to the following statement. Compact fibrosis by itself is not arrhythmogenic, as to obtain source around an obstacle, you need to force tissue faster than the period of spiral wave in the same medium. Therefore, it confirms, I would say, well-known knowledge you can find in many reviews, like in experimental cardiological reviews, that compact fibrosis is the less arrhythmogenic form of fibrosis, but we also put some numbers to it and can explain why it is so. But finally, I want to discuss with you story about, again, diffuse fibrosis, but want to discuss about arrhythmogeneity of diffuse fibrosis. And it also involves our more recent work. And basically for us, the crucial question is the following. Okay, you're given two textures, and then you try to induce arrhythmias, and you find that one texture is arrhythmogenic and one is not. Why? How can you tell what properties of this texture determine arrhythmogeneity? And this is the major question which we're interested in. And in that sense, I would start with a paper of also, by the way, my former collaborator, Sergio Alonso and Marcus Barr, where they told, the following. They had a normal tissue and cluster of fibrotic cells inside this tissue, and they would initiate one pulse of excitation and find in which cases they would get formation reentrant sources here, and how it depends on density of fibrosis. And what they found these bell-shaped curves. Along this axis, we have a density of fibrosis and here probability of arrhythmia. And what they found that if you have low fibrosis concentration, nothing happens. If you have high fibrosis concentration, like percentage, then you have also nothing happens. And there is some optimal fibrosis where it occurs. But what was new here, they for the first time connected it to so-called percolation threshold, which is shown here by a vertical line. Percolation is one of, classical problems in mathematics, which tells that if you have, I don't know, black and white balls, can you go, for example, from one side to another cell only by white balls or by black balls? And if you increase the number, for example, of black balls, sometimes it will be impossible to go from one side to another only by white balls. And what they found that this maximum of this curve is reasonably close to percolation. I would say it's pretty good approximation, look, because it shows only small percentage, just 4% from 100. And you see it estimates it's pretty good. But what was also interesting in that paper, they explain why it is so. And again, and the answer to this is, and it's very easy to understand. I'll just explain it on one slide. It's very, very easy. No, but really, because initially when I saw this paper, I also did not read explanations. I thought, oh, it's mathematics, blah, blah, blah. But then I kind of found, and it's, please believe me, it's very, very, yeah. Like, please look here, two graphs. This graph shows what? Like in cardiac tissue, you have fibrotic cells. If you have a lot of these cells together, they form clusters. And if you have cluster, you can measure perimeter of these clusters. How big is this cluster? And then you ask the following question. Okay, I have a cluster of certain perimeter, I don't know, 1 centimeter or 1.5 centimeter. What is probability to find cluster with such perimeter as a function of number of fibrotic cells? What is probability to find big clusters? You know, if fibrosis percentage is very low, then probability is 0. You don't find, you have just individual cells. If fibrosis percentage is 100, then obvious, every cell is here. You have huge clusters here. Therefore, it's obvious that function of distribution should be how we call Heaviside function, which is 0 at low fibrosis, 1 at high fibrosis, and it has some transient layer here. Yeah? Second question. But you want not only to have big clusters, because if cluster, for example, is very big, it can block and wave cannot propagate at all. But for us, probability for wave to propagate means percolation. Yeah? Therefore, you want to have a big cluster, but you don't want to have blocking due to percolation. One more question for you. What would be the graph of percolation threshold depending on number of cells? Still the same. At low fibrosis, 0, at high fibrosis, 1, and then you have this. But it will be shifted because, of course, for percolation, you have larger clusters than just clusters of normal size. And now let's just put it in normal probability theory terms. I want event 1, provided that I do not have event 2. Means event 1 for me is such function, but I do not have event 2, means 1 minus probability of this, yes? Therefore, I need to multiply this function by 1 minus this function, and then it will give me just bell-shaped function. So for me, it's like very, very natural what they observed here. And indeed, they found that it works, and it gave like qualitative relation between like these two processes. They could explain it. And I also should mention that Ed also has a paper which exploits like this type of idea for fractionated electrograms. But what is done here from a general point of view? We talk about size of clusters. Therefore, when we talk about general theory of reentry, we exploit the idea of critical size, because you need a critical size where reentry can circulate. But for reentry, you not only need a size, but you need a trigger. And trigger for reentry is a unidirectional block. Therefore, you need to have unidirectional block in order to have. And therefore, for us, it would be interesting to create a model or description which will have both, not only critical size, but trigger of reentry in terms of unidirectional block. And this was the paper which we published again a couple of years ago with Farhad Pasha-Kanflo from Hopkins, and at that time he was working in Harvard. And he's a fantastic researcher. I mean, I don't know if some of you know him. He did a lot of MRI, works with Natalia, also with other MRI imaging group there. And also, I think you got silver medal of World Olympiad in physics at some year. Anyway, But just briefly tell you about that research. Okay, we use model, Dust-Mitovich model, and we just did a simulation and found, And then we were interested, or like Farhad was interested at the first instance to see, okay, if you have this texture, let us focus to the center of this spiral and find out what is there. Do we have cluster, or what we have there? And he found that what was in paper of Alonso not exactly correct. He found that indeed he can see clusters around which wave rotates, but these clusters not necessarily need to be joined to each other geometrically. How they should be functional clusters, because there can be small gaps, but wave cannot propagate inside these gaps. Therefore, functionally, for wave, they are single clusters, but geometrically not. Okay, and then you can make some kind of distributions. I will show a lot of these distributions. Again, it's called some name, like horrible name, like CCDF, I don't know. But basically it shows here you have a probability, and here, for example, you have cluster size. And if you have like 10 whatever, then a probability of clusters to have size more than 10 is given by this. More than 100 is given by this. And then by a black line, you see like a geometric way, and by this is functional way. And we'll also do it for different sodium channel conductance. You see they differ, and differ can be quite substantial because of this log-log growth plot. But again, this is not really breakthrough. I think everybody understands it, and I think Sergio Alonso also would understand it. It's like very easy. But what next? How to employ this? And for this, we know, of course, the classical idea of onset of waves in fibrotic tissue is so-called idea of source-sink mismatch. If you have a widening, then you can have a block of wave here. On other way, you have no block at all. And therefore, what we wanted to do, we wanted to mark all possible block points in our tissue. Of course, points, not points with inexcitable, because if you have barrier, of course, it's a block from both sides, but not what we're after. We look for points where wave potentially could propagate, but it does not. And for that, we found such blocks. It can be bidirectional or unidirectional. And then we found such graph, like which was a little bit unexpected for me, because it shows like all blocks, only unidirectional blocks for different, again, excitability. And we see that like most of the blocks are still unidirectional. Again, for me, I would think that most of the blocks would be bidirectional. If you have some problem at one point, it wouldn't propagate from both directions, but not. And amazingly, at least in our textures, most of the blocks, I think 80 or 90% in many cases, were unidirectional. Anyway, but then based on that, we wanted to build up a model and to predict probability of this reentry. And this looks very much similar what people do, for example, for infarction scars. Because, but you ask yourself, okay, now you have this block, you have clusters, what next? Then you would tell, okay, if you have clusters and you have point of block, of course it has two sides, obstacle here and obstacle there. But then you need to decide which obstacle you use, because they have different perimeter. And of course, I think as in cardiology, you need to use obstacle with lower perimeter. And therefore, you will call it minimal functional cluster. And finally, what we considered, because we're after statistical description of this process, not like particular patient, blah, 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 but really if you have like thousands of simulations, what you would expect on average. And then you can say, okay, if you have this block area, wave can approach to it from many different directions. If you kind of lucky and wave comes exactly to the point of unidirectional block, then full perimeter, which would matter. But if it comes from side, then wave will split and part of wave will go from this side, part of wave from other side, and effective perimeter will be smaller. Therefore, for that, we just decided that we need to weight our perimeter with some factor, and given that all directions are more or less same, we just got a parameter alpha, and then we have our main equations, which should predict onset of arrhythmias, that we need that weighted size of minimal functional cluster should be more or equals than the wavelength of reentry. And when we did it, we have all distributions here. We found very good results. We found here like that in black it's real simulations, and in blue our estimates based on these basic ideas. And we found that they very closely follow each other. And we found that all these words, minimal functional cluster, are very important, because if you, for example, consider geometric cluster but not functional clusters, all is wrong. If you use not minimal but just any like functional cluster, is also wrong. But anyway, and minimal functional cluster is also wrong. Therefore, for me, it was like really, I was very much excited about this work, that we, for the first time, were able somehow from not direct measurements of arrhythmia, still find probabilities. And therefore, it shows that it works. Because I would say that on one hand, it may be obvious, because everybody was telling already you that you have like this source sink mismatch and critical size of reentry. But for me, keeping in mind complexity of wave patterns, which we get in fibrotic texture, was really, I was really pleased to see that still this methodology is working. And therefore, we would say that, like in this work, we showed that the concept of minimal functional cluster helps to do it, and to do it at least in statistical way. And then the next, of course, obvious things is try to do it on specific textures and try different procedures of abrasions, etc. But this we didn't do because Farhad now changed. He works with artificial intelligence, etc. And still like not continuing this research. But I think it's very, very interesting. But one interesting question is, but what I showed you was just pure numerical experiment. How we do fibrosis in numerical experiment? You have field, and with certain probability, you say, okay, this cell is fibrotic, this not with some probability, and then you get a field. But what is in reality? And this was the next work, what we has now in the progress. And here we were lucky to get some data, because at Leiden University Medical Center, where I was working, was also Professor Katja Zeppenfeld, and she kind of published a few years ago a paper with full histology of 9 hearts of patients with non-ischemic cardiac myopathy. And then she did a very good staining of all the samples with very high resolution. And she was she kindly shared this data with us, and we started to investigate them. And this work is in progress. I will not tell you final result. I'll just tell you where we are at the moment. Okay, because we're interested in these clusters, of course, the first question for us was to identify these clusters and what she did to measure size of these clusters and so on and so on. And what we did, we also generated the same clusters, but how we did it before in random assignment of cells, like how not only, almost everybody does it in the same way. You have just, and you put fibrotic cells here. And when we compare distributions of real clusters and our clusters, we found that all is completely wrong in our simulations, in that sense that here you have like generated clusters, which means by random procedure, and real clusters. And in real life, clusters are very, very big compared to what you see in these numerical models. Then we kind of wanted to characterize a little bit about clusters itself, because I kind of already for some years have an idea. For me, it's difficult to express it. Maybe you can explain it just on, how to say, like in verbally, because I think that fibrosis, you know, that cardiac tissue has anisotropy. Velocity in one direction is different. But I think fibrotic textures also have anisotropy. That they are somehow aligned, and they also have like, and therefore, we wanted to see what we can tell about this anisotropy. And of course, for this, you can have, for example, just cluster and make for this cluster principal component analysis of main direction and orthogonal direction. And by comparing eigenvalues, you can have like a quantitative value of this anisotropy and to see what direction is going on. And also we did it. And also what we tried to do, we tried to connect it with fiber orientation in the heart. But unfortunately, how to say, we find that fiber orientation indeed predicts direction of fibrosis in mid-myocardium. But then we suddenly found also another explanation, which is extremely trivial again, because, you know, if you have rotational anisotropy in the heart, okay, and if you make a two-dimensional slice, that in any sections, basically, all fibers should be circumferential. They would have different kind of maybe elongation, but from such data, it's very difficult to extract. And therefore, the most crucial for us was to kind of try to extract it from three-dimensional data. And this was also one of my reasons why I asked Olivier to invite me to come here, because you have excellent data about three-dimensional fibrosis. It would be interesting to see, first of all, what are clusters in 3D? Then if you have 2D and the 3D, can you somehow from 2D predict what will be 3D shape? This was of great interest. And for me, because also like our group was the very first group in the world, like again in 80s, who started to study re-entry in 3 dimensions. For me, it would be very interesting to understand what will be 3-dimensional re-entry in presence of 3-dimensional fibrosis, because it's a highly non-trivial question. For example, for 3D, I just put here some questions which I'm interested in, like how fibrosis organized in 3D. Is it possible, like 3D from 2D sections? How you define cluster in 3D, and which perimeter of cluster is important, which drives re-entry, because they have many important perimeters. And I can show you, for example, one of our old papers with 3D fibrosis, where we compared 3D and 2D, and you find that in 3D, period is much faster than in 2D. And this happens why? Because if you have many 3D sections, there is one section which drives all other sections, just due to probability. And therefore, it could be very interesting. Second thing, what I wanted to tell, that on the way to you, I visited one of the most famous French institutes in exact science and mathematics. This is called IHS. I don't know, but it kind of has the largest degree of Fields Medal laureates in the world, and it's really exclusive place, like for physics, not for medicine, but it's like really. And there I have long-term, I mean, how to say, wouldn't say collaborator, but person with whom I talk for many, many times, Professor Gromov, who is a world expert in geometry, in mathematical geometry, like so-called Riemannian geometry, blah, 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 blah. And when I told him about these problems, he became extremely excited, and he told me that he sees very interesting mathematical questions from this line of research. They probably still would be very far from real clinical applications, but he told me something like that. But if you have like these complex structures, this perimeter of these clusters, can you characterize them as a mathematician? And also, when you have ablation, because for me, it's really, I tell everybody, like, I give you this texture. Tell me how many points you need to ablate to remove arrhythmia. I mean, 2 or 2,000. We don't know even at such scale. And therefore, he says that also this distribution is very interesting, because if you know in mathematics, this percolation problem is a very important problem, and mathematicians are working with this. He also told me that there is one very like famous mathematician in Lausanne who works with this percolation. He will contact him, but in general, he is like very much positive and interested to have some meeting with the people who do cardiac modeling, cardiologists, with mathematicians. He really wants to promote this research between mathematicians. Okay, good. And finally, I have questions I ask a lot of biologists and cardiologists. And this question is, but tell to people and tell, please explain me, but how fibrosis occurs? Does it occur at single point, or it occurs everywhere, or what is the time course of development of this fibrosis? And second, I also talked already again, that for me question is, when I talk to clinical physicians, they tell, oh, Sasha, I know that fibrosis is different from different cardiac diseases. But when I ask them to tell, but tell me how different, they cannot tell me. Therefore, it's like really interesting to know. And this is not just a simple question, because we already have in our group models where we can really model cells and cell development, how it shows, for example, here, like cell, they can move, they can divide, etc. And theoretically, we can create a real virtual model where we have a cell, where we have a fibroblast, that this fibroblast will produce collagen, and then we can really try to reconstruct this time dynamics in reality, and would be very interesting for us. Okay, so that's all. Okay, thank you.
Thank you very much, Sasha, for this very inspiring talk. Any questions?
Thank you very much. Yeah, so towards the end, you're talking about these clusters in 3 dimensions. What kind of resolution do you have an idea of what you would need to capture these clusters from the experimental data? Because you mentioned in the models, I don't know what the resolution of your models were when you compared the cluster size, right? You said that you had smaller versus the clinical, but what's the optimal resolution do you think that you would need?
Yeah, again, I have obvious answer, the lower the better, but what I saw in Olivier, institute, like in Rick's Institute, that it's kind of, you have a data with resolution of 200 microns, and I saw you can reconstruct the 3-dimensional geometries, and it's very good to start to look at it, because cardiac cell, of course, like 100 microns. So, but and then yeah. See, but data what we have high resolution, but for 3D it's excellent to have it 3D because again I have no idea how they look like in reality.
And the other thing is like clustering from my experience with some of the modeling is that the fibrosis in some cases we rule it not that dangerous, but just for the initiation part it doesn't play a role, but for maintenance as well, the clustering size versus initiation versus maintenance. I didn't get a lot of that through a lot of the fibrosis stuff, but the focus on, even though that it doesn't initiate the arrhythmia of these clusters, they still may be bad in the sense that the maintenance could be very important as well. So I'm not sure whether you distinguish between the two versus initiation versus maintenance of the arrhythmia for the future cluster studies.
Yeah, like of course many questions here coupled together. So first of all, I would say that word cluster by itself is also heavy use in other aspects, because like we also collaborate with mathematicians at Imperial College, and they also, for example, want to find clusters of our clusters, for example, with different complexity, like to have like this phylogenetic tree of these possible clusters, etc. But in terms of initiation and maintenance of arrhythmia, yeah, it's kind of interesting question, like interesting to discuss. I mean, what to tell, I was working on this a little bit as part of our research, and we see sometimes, but very consistently, very strange results, which means the following. If, for example, you would have areas with low excitability or areas with more fibrosis, areas with less fibrosis, somehow in our simulations, source of arrhythmia tend to move to the regions of higher fibrosis. And I mean, I have movies, and I don't know why it's exactly opposite, for example, to what Michelle Hatziger sees like in this ventricular fibrillation, where it has acceleration of ventricular fibrillation. In our, it's this. And normally, what we would see, like, look, one story, if you have, for example, these clusters which initiate few initial beats, which initiate arrhythmia somewhere else. This is one scenario. But but in general, I just don't know. We normally see that all these clusters and other things, they really somehow attract arrhythmia sources. I just don't know. Like we have also a long line of research. We even like did some crazy experiments where you can have actually discussed with the review when we met in New Zealand, if you remember a long time ago, that if you will make, for example, a low excitable area close to the base of the heart, in our simulations we often see that if you have single spiral wave, it somehow drifts to the end of the heart and disappears. It's very, very repeatable in our simulations. I don't know what is the reality. I was asking Olivier, what of that is possible to do in experiment?
Sasha, thank you very much for this very interesting talk. Two few points. First, don't be disappointed when we presented our data in 1996 at HRS. At that time, it was NASP for PV triggers. Our American colleagues were saying, okay, French guy, you are nice, but you are drinking too much wine in Bordeaux. It is not possible to have trigger coming from the pulmonary vein. So I completely join you with this discussion with Natalia. Sometimes, you know, when you are a little bit disruptive, it is difficult to... Second, just I want to put my clinical aspect and to put it in relation with what you said. When we have a re-entry in the heart, whether it is in the atria or whether it is in the ventricle, when it is what we call a macro re-entry or localized re-entry, you need different things to have this happen. First of all, you need a kind of compact fibrosis to really create a kind of obstacle and to create an isthmus where the impulse will slow down, propagate, but very slow, and then accelerate around this obstacle. whether it is in the atria for macro-oriented tachycardia or for ventricular tachycardia in the ventricle. However, when it comes to fibrillation, whether it is in the atria or in the ventricle, I think the tissue characteristics, clustering of this fibrosis size is really different depending on if you talk on macro reentry, something regular, or something polymorphic, more fibrillation. And for example, in the ventricle, when you have patients that have myocardial infarction, when you have a dense scar with no surviving tissue inside, as you said, it is not that arrhythmogenic. You need to have surviving fibers in this dense scar to have something that propagate and create a reentry. And when it comes to fibrillation, ventricular fibrillation, for example, you have this really two categories of patients, VT and ventricular fibrillation. But you have also a population where you can have both. And it often happens, ventricular fibrillation often happens at the border zone, where you have tissue characteristic, which is not dense scar. It's in between. You have kind of functional. When it comes to ablation, again, it's not 1 point or 200 points that matters. That really matters is to kind of homogenize this fibrosis. Whether it takes you 1 point to do it with ablation, or whether it took you 100 points, I mean, it's not really that important. It's really to clean the tissue and to make it less arrhythmogenic. So that was just, I have no question, but just to have your...
but I completely agree. Like when, I remember when I was a student, when my supervisor, Arkady Pertsov, who later became also Olivier supervisor, told me, like, Sasha, like it was like, again, around 80s, in the heart, the most dangerous, not the tissue, but how the tissue. Again, I think people understand it already for quite a long while. And probably like some kind of anti-arrhythmics, like, I don't know, class 1, etc., they can maybe even make tissue more dead, and then it prevents it. But I mean, I don't know, like, how to say, I kind of see in my research, I do it already for a long years, and I see more and more similarities between different topics. For example, the most simple, of course, is isthmus in compact, and then you just ablate it and so on. But then you can say, you may have many accessory pathways, and then you have many possibilities for different types. And for me, all these are closely related issues, like one isthmus, two isthmus, but when you have 1,000 isthmuses, or like you have what I showed you, a lot of this fibrosis.
Although even if you have multiple isthmus, it's not that so many scenarios. As you say, at one point, you have a kind of attraction of the impulse to somewhere. So in fact, there is not, even if you have different isthmus, there is not 100 possibilities. It will still, the main wavefront will still find its way to propagate into a kind of probabilistic route.
But I completely agree, and probably it has like, actually I don't know, but in isthmuses it tends to the minimal period. Yes, always it should, but I kind of...
And the other thing I wanted to point out also, you said we need a certain amount of fibrosis to have arrhythmogenicity, right? We saw it on the VF patient, for example, the work we publish. You need a minimal size of patchy fibrosis to have fibrillation. Right? But it comes also to ventricular fibrillation in terms of tissue characteristic. For example, to have VF include using only the myocardial cells, maybe in terms of excitability or whatever, I don't know how many cells you will need to actually have an arrhythmia using only myocardial. while when you are talking about Purkinje cells, the excitability level threshold is different, and probably the recruitment of number of cells that are needed to create something is also very different. This is, and the same, I think, applies for the pulmonary veins and the atria. Although these cells, we know they have specific properties. So I think it's also this interplay between two different tissue.
I kind of what I want to say that when we do our mathematical studies, we kind of don't know how close we are in reality. And for me, it is amazing that in modeling world, nobody still did not do good scaling procedure like what you tell, what should be a minimal cluster of fibrosis to have something, or even like what you ask, what should be MRI resolution, which will be sufficient to predict anything. Also, for example, even in fibrosis modeling in our group, what we try to do, we try to model fibrosis on cell-based level. Therefore, they are really inexcitable, or collagen really inexcitable obstacles, and so on. But what, for example, Natalia Trayanova and many other groups are doing, they change diffusion coefficient, and they can also. And when you change diffusion coefficient, it's completely different scenario of induction arrhythmia than here. It's much more easy to induce arrhythmias when you change diffusion coefficient. And all these questions just we don't know because, and I can very well understand if, for example, in our modeling, our pictures are more complex than they are in reality. It may be, but it needs to be studied. For me, it was also a little bit also interesting. We had a very long discussions with Vadim Fedorov, and we know his ideas about atrial fibrillation, etc. But he also told, like what you told me, that he also sees in many patients isthmuses during atrial fibrillation, and single ablation can really help it. Maybe indeed situation is more simple than we try to do it in our models. It needs to be studied. But but probably, as always, like what people say, there is no single ventricular fibrillation. There are many different types of atrial fibrillation. And it's what we are doing for research.
The imaging we have here, the facility we have with the 100 micron resolution, can definitely
because it would be the
I had just a question or a comment based on what you just said, because at the moment it's a pure geometrical analysis, right?
Yeah.
But you mentioned the work by Natalia. She not only changes diffusion, she also takes into account electrophysiological changes due to paracrine effects from the fibrotic, from the myofibroblasts to the myocardium. So it's not just non-excitable, excitable cells. The excitable cells around the fibrosis will have different properties from away from the fibrosis. So I guess you don't have the answer, but this will tend to increase vulnerability to arrhythmia or decrease vulnerability to arrhythmia?
Yeah, in general, any heterogeneity should increase vulnerability. And of course, extremely important issue about effect of fat, because and like many people after that. And also like, I don't know, but for me, even like more classical problem of gray zone in a function area, like, I don't know, most of people still model it based on initial paper of Natalia, where she changed like 3 ionic currents. But of course, it varies a lot, and it can be completely different heterogeneity around infarction scar. Increasing level of complexity is of course very interesting.
Okay. Any other questions? Mark?
You mentioned fibrillation stabilization due to fibrosis, and you said that it was due to slowing of conduction. But would you all be able to achieve the same with a global reduction of conductivity?
But it is the same. in a way, fibrosis, initially we started to model not fibrosis, but we really was studied the reduction of connectivity. For example, each cell has 4 neighbors, but you randomly remove one of neighbors and together it's the same effect. Yeah?
But if you just reduce connectivity parameter,
You mean the space or diffusion condition?
they don't get diffusion.
Yeah, exactly. And this was like, what for me was very amazing. And I was asking a lot of my colleagues who do mental modeling, did you see any model like whatever, in which increase of space and promotes like that, not increase? Nobody so far told me about such models. Because in that model, effect can be different. In that model, fibrosis can increase. It makes the situation worse.
But again, what is funny, in clinic when we try to do ventricular stimulation to induce arrhythmia, for example, in patients in whom they have fibrosis due to hypertrophic cardiomyopathy, myocardial infarction, whatever, it's quite, the threshold to induce arrhythmia is very low. You can induce it very easily, whether it is ventricular fibrillation or ventricular tachycardia, depending on the fibrosis status. But when you have patients with almost no fibrosis, at least that you don't see at the MRI with this actual resolution, it's extremely difficult to induce ventricular fibrillation. You need to pace extremely fast and at a very abnormal physiological response to have something. So you need to induce to have at least a little bit amount of functional block, fibrosis, whatever, but you need some. That's exactly. But how it relates, as you nicely show, if you would have the chance to take a picture of the first figure, the work you are doing with the heart from Katia, and trying to look at your simulation and the location of fibrosis clustering and so on. I found it fascinating.
But by the way, I didn't tell you, but one of the problems that we want to solve, because cardio would have a lot of epicardial problems. And what we would like to do, if based on epicardial and endocardial arrival times, the chance say about fibrosis inside the it's a possibility.
I look at this actually in terms of, for example, just cycle length. I had patients who study during ventricular fibrillation and actually having the catheters in the pericardium, another one facing that side endocardium. For example, for myocardial infarction, you have fibrosis, and we induce ventricular fibrillation, and during the first 5-6 seconds of ventricular fibrillation, you have a very small gradient between endo and epi. It was almost activating exactly at the same cycle. And you need, as we say, to wait few seconds, 10, 12, 15 seconds, to start to have disorganization, and then epicardial slower than the endocardial.
But you're talking about what if you do in sinus treatment? Can you say something about the process? Because in sinus treatment, again, if you propagate through fibrotic area, you have
You have delay, definitely. You have delay and zigzag activation, like Jacques de Matt have nicely shown. You have this kind of zigzag activation with delay the potential on the epicardium.
But it's kind of.
But it will not tell you about the nature of the fibrosis, because whether you take myocardial infarction or ARVC or hypertrophic cardiomyopathy, it seems that the electrogram signature, whatever the type of fibrosis, is the same.
But what do you think are sources of treatment?
It's an entire symposium.
I would say, for example, this classical work of Peter and I think of they never saw rotas on the ship. I always saw like very few patterns, etc., which would together has really much of neural nature. You think it's the same, yeah?
But I mean, when we use the CGI, which was the best to try to capture the entire activation, in fact, we knew that. I mean, it's not you saw kind of water from a global picture. It's like a satellite view, you know, from a storm. But when you dig deeper into it, it's probably not that that picture of water. It's probably breakthrough and so on. That's
But which breakthrough?
yeah, and especially when the rate is.
Yeah, because if you think about filaments, about activity, but again, today, like in each group, so one more time, like human heart, it has so many technical muscles, like the heart, etc. It can also be a lot of it's very cool.
But this you see on the histology from Katja.
Yeah.
Even for Rick worked a lot on the moderated band in the right ventricle, which is a band which is a bridge between the septum and lateral right ventricle, but you do have also this full standard in the left ventricle, and without any fibrosis, just maybe by stretch or by the content within this fibers in small packaging, you can have ventricular fibrillation, definitely.
But also, like, but would you agree? Because some people told me that if you just push by finger to start and stuff.
Oh yeah.
That's why.
The things on stretch and pressure, I mean, we haven't yet, don't fully understand. When you look at sudden cardiac death, the majority of sudden cardiac death, 60% of sudden cardiac death occurs during night. Of course, you have the sympathetic autonomic nervous system as well, but I mean, the impact of, we know for atrial fibrillation, for example, patients who have fibrillation, when they sleep on the left side, so they are pushing, they are putting a lot of stress on the heart, they have we know that, positioning.
Oh.
Yeah. So we still have a lot of opportunity.
Yeah.
Okay, thank you, sir.
Thank you very much.